Hello all, I hope you all are doing fine, and this is day 26 of the training in the FPGA development, and today we are going to discuss about FIFO implementation again, but in the terms of actual project implementation. In the design of FIFO, we should also simulate the test bench as well. I'll try to explain the test bench Verilog HDL structure and the actual design of the FIFO structure such that you will actually understand the architecture of FIFO functionality through each block of the Verilog HDL functionality. So let us go to the today's agenda. With that being said, recap of FIFO implementation and recap of the FIFO implementation, like first in first out implementation, read and write operations in the memory of the FIFO. We all know by this time FIFO consists of RAM and also block diagram and architecture of FIFO, that what are the components inside them and how they are connected and what is the functionality that happens after the simulation, how do we get the output or how do we write and read the data, and we will also understand the design Verilog HDL file and test bench Verilog HDL file. So let us go to the introduction of the FIFO. FIFO is normally an input output buffer that which allows data bytes to follow through. So if you have a FIFO, in that FIFO kind of implementation, what it takes is it takes data and it processes it. It has some set of stack, and in the stack of registers it flows through and it comes out of that FIFO. In the FIFO, the bytes of data is loaded and stored in stack of registers, then sent out through the output port. That's what I have explained just now. FIFO application is used mostly in communicating between two different modules. So this can also be almost in the most UART protocol, SPI protocol in the buffer stages. So that kind of protocols we can implement. So also in the most I2C, not I2C, but UART. UART protocol is important, and SPI protocol. These things, for those protocols, FIFO will work absolutely fine. So that can be implemented there. And in the FIFO, we have called key elements called the pointers that take the form of binary counters. So here in the pointers, we can see we have seen a tail pointer and we have also seen head pointer. It's nothing but head pointer is for writing, and tail pointer can be of reading. Whatever, however you want to describe them, those can be pointers. So these pointers are really helpful for giving the address locations for write process and read process. You have seen there is a write pointer as well. Write pointer is increment pointer and read pointer is read underscore pointer is decrement pointer. Okay, the counters are responsible elements for generating addresses internally inside the FIFO. Internally these addresses are produced, so there will be no external address signal located. Here for the FIFO, we are not giving the address signals for like in the memory. For the memory, to access the data or to read the data or to write the data, we are looking at address locations. So that address location is given manually by us, but in the FIFO these address locations are generated by write pointer or the read pointer. Okay, so that helps in read and write process. So from which particular register of the RAM memory we are reading the data, or to which particular location of the memory we are writing the data at particular location. That location is given by the counter. So counter acts as write pointer and counter also acts as read pointer. Counter underscore FIFO that we have implemented in the single clock design in the last session. As this process of address pointing is automated. Okay. Also, we know that FIFO has RAM, up down counter, flag logic, static memory, all these things. We have seen that. So, the address locations, this is just a recap. I will quickly walk through, and are generated by the counters. So, that's what I have explained. Address is internally generated by the counter. These counters are not two counters, those are both one. Only we have only one counter. We have only one counter, but it acts as write counter and also it acts as read counter. That's what you need to understand. And for separate read write operations separately. That's what representation. So you have static memory for the initialization of the flags and all, for the address location at 0 at the beginning, and from there whatever signal is enabled, for example if it is read signal enabled, it goes to the read counter, and from that read counter it will check the address location, whatever it gets the address location. If address location is equal to 8, then it goes to the 8th address location and then it will be checking it. 8th address location is represented as 7 because it is starting from 0. Okay, so data is coming out into the data underscore out or buff underscore out. Okay, so that is what the definition is. As you have seen the input, output, write enable, read enable, write clock, read clock, all these things you have remembered, right, in the last session. Please watch that session if you can't understand this a bit faster. And you have counter, whatever the signal, if read counter and if write clock, if write clock is enabled and write enable command is 1, then for that memory write enable is there, and now the clock is with respect to write underscore clock. Got it? So for those two things, your RAM will be accepting the data from data in this manner. Follow along the red line here according to my cursor. So at the particular location of the write pointer, here this is write pointer, that particular address location initially it is 0. So that is what static memory is doing. Got it? And that is the write process. Vice versa, read process will be read enable and read clock will be designed, and that will be going from static memory to read control and to the read pointer. Here this output is read pointer. Okay, that read pointer will be accessed in a bottom up approach, and that data is sent to the data out and data buff out. So meanwhile the static memory will check the conditions between this counter and the memory, and it will say okay, full is 1 or 0 and empty is 0 and 1. So you will decide on it. Then that is what static memory is used for. Static memory is used to initialize the counters. That's it. Okay, now coming to the actual understanding of what is full 0, empty 0, full 1 and empty 1. You can see the full and empty are the status signals representing, like acknowledgement, as I have said in the last lecture. Acknowledgement, something we need to understand from the FIFO logic. If you have a FIFO hardware, right, it should communicate for us, because until unless we can't read or write, Only if we have this flag empty and full, then only we can understand, okay, we can read if it is if it is full, or we can write if it is empty. You can write on an empty paper, or you can fill the shelves if it is empty, or else if it is full, there is no space left, and where will you write? You can't write. That is the basic understanding in these 4 paragraphs. Let us uh, stay focused. In the full zero, if full zero, then FIFO can be empty, also have some data, and not completely full. Full zero means, okay, full zero means this entire RAM, FIFO RAM, right? FIFO RAM inside FIFO. Full zero means not full. Full zero. Then FIFO can be empty. It can be empty. It is not full, right? But we don't know what is empty here. We can't declare empty as 1 here. So we can't say this is completely empty. We are just saying full is equal to 0. That's it. That means it is not empty, or it is not full. So there can be some data in some other register. Okay, even one register, but remaining all can be empty. Likewise, if empty is equal to 0, that says if empty is equal to 0, forget about the previous one. Forget about the previous one. The previous one is, if empty is equal to 0, then FIFO will have some data and may not be completely full. Don't by heart these guys. Understand the logic behind it. If empty is 0, empty 0 means there can be some data. Will have some data. May not be completely full. In this case, may not be completely full, or may not be completely empty. But here, it empty is 0 means may not be completely full. In the same way, if full is equal to 1, then FIFO will have full data. Full is equal to 1. FIFO will have full data. Now full is equal to 1. Third condition. Full data. Okay. Then what happens? Full data and not empty. Ready to be read or write to the buff out. So what it says, if full is there, I mean every register is full, what you can see is you can read from it. You can read to the buff out. You can read to the buff out from the registers. From this data is sent to the buff out. That means reading. We are not writing into the memory. Now empty is 1. Empty is 1 is everything is empty. Let me make with a bigger 0. This is 0. Now empty. Empty is equal to 1. Last condition. Empty is equal to 1. Then what it says? Then empty is equal to 1. Then FIFO may be empty and no data. Completely 0. This states completely 0. We will have a clarity. Okay. So if it is completely 0, right? What can we do? We can write in this condition. Okay. That is what flag. If this FIFO, if it is not telling us what is full and what is empty and what are these acknowledgement signals, flag logics, if it didn't say, how would we know? we will never know. So that is flag logic. Okay, so coming to the read and write operations of RAM, let us consider only RAM. What are the inputs? We have data input, and the address is internally generated by this thing. Now we are considering only RAM. Let us consider only RAM. So what are the inputs? Write process is happening. Write process will happen only when write command is 1, address is at 000, address should be at 000, and data input is F9 or C9 or any other data, B3, or it can be 32, any other thing. Simple representations. Any data can be there in that location, in that address location. Read process means read command should be there, like read command signal, write command signal, or we can say this read command is equal to read enable, and write command can be considered as write enable. Guys, I'm changing the names because you need to understand the logic is same, but names are changing from different examples, because in some certain projects, in various projects, all these names will be changing accordingly, so you will never be sticking on it. But what you need to understand is, for every memory you have a reset clock, you have a reset, you have a clock, you have a read signal, write signal, to say okay, write onto the memory, now memory is enabled, read onto the memory, now memory is enabled, like data out and data in. These are the signals. And also we have to consider the address. In normal memory designs, we will consider address as a manual input. Now the address is automatically generated. Okay, I hope you understood the read and write process. In the writing process, the data from the buff in or the data in will be at the starting point, that is for RAM, which then static memory is equal to 0, address is equal to 0, full is 0, not full, empty is 1, okay, it is completely empty. Then only writing process can be done. And in the FIFO operations, we have synchronous FIFO and asynchronous FIFO. What is synchronous FIFO? Write clock will always be equal to read clock, and asynchronous FIFO, write clock cannot be considered, not considered into the read clock. Asynchronous actually does not represent with the read clocks. So we should note here that write enable and read enable are write and read command signals. That, as I have said, this write and read command signals. So in this way, we have data in or buff in, data out, buff out are the data input and output signals. So however the data is transmitted there, and flag logic generates the full and empty signals to the acknowledge whether FIFO is full or empty, and address signals is unavailable as it is already existent in the internal generation of the address by the counter, because address signal is not given manually by us like for a memory design. Now it is FIFO. FIFO means with memory design we have some external modules embedded or integrated to the memory, and we are using that memory stack of registers for data transmission in a sequence, in a series. So for that you can understand write process of the FIFO will be looking like, now write at the write clock is 1 and write enable signal is 1 and data input is 1. Okay, for that you can see static memory, static memory initially it is 000 address, and now at this location, at this all these points as data in, whatever the data you have, let us say D1, that will be going, and that D1 will be C9 here. So how it goes? It goes from static memory to the write control, and in the write control it considers the write pointer here. Write pointer means it increments, as we have seen in the previous lecture how this right pointer happens. So when the right pointer is happening, the data flows here into this thing. And for the next clock cycle, I mean, this is one clock cycle, and for the next passage of the clock cycle at this point, now data can be D2, and that can be stored in this point, and but the previous data will be pushed forward to the next location. That is how address locations are incremented in a downward fashion from the top to bottom. You might have 64 registers, or you can have 1024 registers like this. How much of RAM you have, you can have. But based on that, empty and flags are decided for the write process. So you can see empty can be 1 and full can be nearly 1. Maybe some data can be there for writing, but it should be equal to 0. It can be 0, equal to 0, but it can nearly be 1. Somewhere or the other, some registers can have a few bits of data, but empty registers, empty flag should be 1. If it is empty, then your entire RAM can have a write process. For the read process, empty should be 0. I mean, it shouldn't be empty. It should be full data. When it is having full data, when everything is written, for the full data, the read process happens. Okay, that is data out or buff out. And when read enable and read clock is given for the 1, if it is enable, for every passage of the clock cycle, the data will be read out to the buff out, and you can simulate that in the test bench. So that is how the design of the Verilog HDL functions. And now let us write the Verilog HDL codes for the FIFO design. Let us now look into the development of Verilog HDL of the FIFO design. So create the test bench to simulate the created design. Available pins and internal modules should be known first before writing that, and we have write enable, data in, and address internal that should be represented. Read enable, data out, clock, reset, full flag, and empty flag. Those should be known to us. And you can see for the part 1 of the design in the Verilog HDL, the declaration happens module, FIFO, clock, and reset, and write enable and read enable, data in and data out, full and empty. And you can write inputs. What are all the inputs you can see? Write enable, read enable, clock, read, reset, and input data in, D in, and data out is D out. Earlier in the last lecture, we have written data underscore out, data underscore in, or buff underscore in, or buff underscore out. Now I have changed D in and D out. See, why did I change these many times? Because to make you understand, okay, this is not a particular design entity. You should only represent with D in for the data in. No, you can represent in any way, but you should follow whatever you represent in the input and outputs, that you should be following throughout the Verilog HDL code. Likewise, you represent the output. In the same way, whatever input and output you have written, write it in the same fashion till here for wires and registers. So all the inputs are wires and all the outputs are registers. Okay, and full and empty can be registers again. So you will understand in the coming design, but these can be wires if they are indicated at the input as well. But let us consider an integer I for the future purpose. If you don't understand this, or if you forgot to write integer I, you will understand in the particular procedural blocks you need some integer value, k, I, or j, any other thing that can be added in the top of the representation in the declaration itself. So now assign the values for the full and empty flags. When will be the full and empty flags are enabled. For full flag, the address can be 5-bit binary 10000 at that location, at that peak location. For that address location, you will be getting full is equal to 1. I mean, when address is going to that position, for example, you have 5 bits and 5 bits of address locations, like you can have 32 registers, and in the 32nd register, if it goes to the last point, end point, address pointer is at last pointer, then you can see 5-bit binary 1000. It represents 2 power 5. That is the value of address location of the end point. End point address location is 1000. It is not the data, guys. It is not the information. It is just only location of the address. Okay, but data is represented in the registers format. You can have 8-bit data. That is different. Usually, if your address location, see, you can see in this representation, see, if it is the 32nd one, see, all 3 ones is representing the address location, but the black ones with the boxes, it is data stored in that location. Address is a location. Okay, in that empty will be in the same way. When address pointer is at starting position at 0 0 0 0, at the starting position, then you can say empty is 1, or else empty can be 0 if it is 1 or if it is 0. Got it, guys? Always at the rate passage of the clock. In the next, the procedural block begins. After declarations of registers and wires assigning the values, we can go to the always block at the rate of passage of the clock. You can start the begin and end with it, and for every begin and end, you need to mention all these begin and ends here in the particular fashion. You write for every begin, you write end. Okay, begin if reset, begin address is 4-bit binary 000 at the starting point, and at that starting point, or you can also say at 5-bit binary 000. For I is equal to 0 and I is less than or 15, I plus 1, that is increment. This is a loop now. So memory of this I, for every bit of I, your value will be incremented. 8-bit binary 0 or 8-bit binary 1. So it is incremented, and then end the process. If it is reset is equal to 1. Okay, if reset, when reset, entire design is 0. So that design has a binary value of 0. Then else means if not reset, write enable or read enable, or this is or operator. If write enable is equal to 1 or read enable is equal to 1, you can read and write at the same time. You can read and write at the same time, but we should mention the specific condition when write enable is possible. Only write enable writing process. Write process, not full. Then whatever data you have, that can be sent to memory address at that location. This is how write process is happening, right? From the data input, it will go to the memory address, and then address will be incremented for every loop. right? So in the stack of memory, if it is at 0, right, now the data from the data in, it is went to memory block, and then from that memory block, memory of 000, it is written, and immediately address will be incremented. Address will be incremented to 001, and if there is new data, that will be stored in this pile, in this second register. That is how write process is happening. And end it. If you begin, you end it. Then else, if read underscore enable and underscore empty, like for the read process, you can see, you can read the process like this. So whatever the value of mem0, it goes to data out, and for the mem0, now mem0 is empty. Mem0 can have the value of mem1. From the mem1, but not empty means, for reading process, entire memory should be full. See, full is 1 and empty is 0. Understood, guys? So mem is equal to mem of 1, whatever the data in the previous state, that comes to the next state until the you have the 15 registers, that 15 locations you get the data. And in the final stage, whatever the leftover piece of register is there, that can be given a default value of 8-bit binary 0, and address is decremented every point of time. Address is decremented. See, in this process address decrements, or in the write process address increments. Got it? So that is what, in the read process address decrements. And end the block. There ends the end module. Design module is ending now. Let us go to the test bench, so you will better understand this test bench in the EDA playground. Let us open. So now consider, you have seen this. Yeah, consider the test bench, and for this design you can see read process is done in this format. The memory, whatever the memory is there, that memory is sent to the data out, and whatever the write process, the data in is going to the memory address. Okay, for every memory address, mem square brackets 1 location is nothing but this is a location. Okay, this is the design file that I have explained just now. For this we have to go for a test bench simulation. In the test bench simulation, you can see this tick time scale and module declaration, registers and wires, and instantiation of the design with label and the design. This FIFO should look like this, and then after that you initially set the clock as 0. Initial clock should be 0 at the reset point or in the beginning point, that is called initialization, and clock initialization is done. After that, begin and end, go to the task. In this type of project, now we are introducing new type of test bench task, like we are writing task for each set of operation. For example, for reset there is a task, and for write there are tasks, read tasks. So every operation is verified based on the task. And first task is reset. Task reset. Begin it when after 10 nanoseconds. Reset is 1. We have said that. Now reset is 1. After this is executed, display that okay, reset initialized. You need to give some acknowledgement to the reader, right? After display, have some initialization message. Okay, that is done. Then again, after 29 seconds, make the reset to 0 with 29 second delay. 0 and end. End task. When you write task, you need to end task. And if you have more than one statement, begin and end. Always. Okay, that is how Verilog HDL structure you can write. Come to the next always block. After 5 nanoseconds, your clock should be enabled. How will you enable the clock? Initially clock is 0. Now your clock is 1. Why? Because negation of 0 is nothing but 1. So now your clock is 1. Right? Now let us do the task verification of write. So you need to initialize the write and read task like you have done for read and write at the both times. So write and read. Write and read are both enabled. You can read or write. Anything you can do. Like that, for beginning, both write enable command should be 0, read enable command should be 0. Then data in is also 0. There will be no data in flowing. Data in is 0. So then you can say write and read and initialize is done. That is processed. Similarly, begin and end, and you have written task, end the task. We have done 2 tasks now. What is that? First task is related to the reset. Second task is related to the read and write initialization. Okay. Then third task is writing it. What do we want to write? We want to write something. Write something onto the memory, right? Then input w underscore data. Here we have given some data and begin it, and we have given some register here, write data, and passage of the clock at always at the passage of the clock, begin it, and write enable is 1, write enable is 1, write data to the data in, write data to the data in, some random data you can write to the data in. And now likewise for this task, you have created a task, right? You will use this write command here in this write task. So once you set the task, you can reuse it in the second thing. Okay. Then data in is equal to w data. Now what are we writing now? We are writing values of 16 values onto the memory. Whatever we give to the data in, that data in will be writing data to the memory address. See, this w data whatever the w data we are getting, that is going to the data in, and that data in is transmitting data to the memory address locations. Relate the test bench with the design. That's what I'm explaining. So this task is done now. Okay. Now again we are writing 16, write 16 values in this same similar fashion. When you begin, end, and how will you write? You are using write task. That write task is obtained from this task write. Okay. You have given 16 values. All these 16 values will be executed, and F, E, D, C, F, B, F9, whatever the value there after the hexadecimal, you can see. And if I can change this to CF, and I can see what value I can get, I'll this is my own data I am giving. That data from this write will go to the write task, and in the write task what we have given, write enable is 1, and whatever data write data is there as an input, that write data is, I mean there will be an extension to the data input, so it is sent to the data in, and now this data in having information that I am giving. Okay, now this is there, that will be considered in the design as an input to the memory location. That is how write process is happening. Similarly for the read process, once you write it right, you have initialized right, that you have to end task end write enable is equal to 0, d in is equal to 0. There will be no data at the d in. There ends the write process. Now read process, task read, when it will be read, only read enable is 1, And you can say task read 16, you can mention 16 times for the reading and begin and end the task. Now this task read 16 is our process of reading. Then end the read by saying read enable is equal to 0. Okay, so after write and read processor ended, you can say initial begin display start initializing, and write and read init reset. So you have to mention all these things. First task, what is the first task? Reset. And next task, write and read init, that is return write and read init. What is the next after write and read init? Write, starting write. So for that write, after write you have write 16, you have to write 16 information values, write 16 and end write. Now give some time, after 2 nanoseconds come to the read 16. How will it read the 16? Read 16 is nothing but read enable at 1. When read enable is 1, what is the value? When read enable is 1, whatever the mem value is there, that is sent through the data out, mem1 to the mem0, mem to the mem1. When it is full, not empty means it is full, all these values will be stored to the previous one. So 1 will be decremented, 2 will be decremented, 3 will be decremented. Whatever the value 4 is there, that is pushed forward to the top one, memory third location. So hence it reads all the 16 values. All the 16 values. It is read. And now end the read. Now begin and end read clock. You have to end the read. That end read is given here. Now dollar display stopped. Process is stopped after end read. You need to dollar stop to stop the simulation, entire simulation. For the waveform generation, it is a mandatory process when we are using EDA playground. Okay, now I will try to run it. Hopefully, fingers crossed, we will get the output waveform. Yeah, we can see. See clock, at every clock passage of the clock or every clock, you can see data in is getting at CF. Did you see at CF? That CF, I have given it the value of CF. This is how it is related. You have to give the data in. How will you give the data in? Data in can be given by writing some data. That is why we have written writing some data. How will you write the data? Like a task. This is one representation. Remember this, these two tasks. Very good understanding of this task is required. These two tasks will make you write something onto the memory in the test bench. If you can understand in this way, this can be replicated n number of times in your entire real-time projects or wherever you might have been asked. In the design, you are writing the write process, very good. But for that write process, we are giving some additional logic, additional hardware realization in the test bench environment, like writing the data. And for that write task, input should be write data. For that write data, whatever write data you have, that you can give into the data in. So this write is connected to W data, and for that W data it is connected to the DIN, and this DIN is connected to the design DIN, and that is connected to the memory address location. So this is a chain. Now if you can see the waveform, data out will be checked at reading position after write, after 2 nanoseconds. Okay, after 20 nanoseconds, like I mean 20 picoseconds, if it is 2 nanoseconds, you can see this this full is 0 for the, at the reading position. The full is full, you can see full is 1. When it is full, you are sending the data to the buff out when full is equal to 1. Okay, when it is at 1, full is equal to 1, and read enable is also 1. Now from this your read starts, from this your read starts. But when did the write started? Write started from this point. See, from this point write started, CF. Okay, initially the clock is 0, I mean the reset is 0, but before that the reset is 1, clock is 0. And W data, you can see the whatever the W data is there here temporarily, that can be given to the next. If it is mem1, this is mem0. If it is mem2, it is mem1. So like that your data can be stored in this way. So I hope you have understood the realization of this, and you can see the flag variations. It is variating from flag 0, full and empty, full and empty, full and empty. And when will be the empty? Empty at the end. Empty is at the end, and in the beginning also. Empty is 1. That is how memory works, right? Whatever the data is sent through the data out, you are having no longer data. That is the meaning of empty 1. Okay, so I hope you have understood the test bench simulation and entire design of the FIFO. You can also see the design in this bottom thing, where you can see at clock initialize, start, reset, write, read initializing, stop the data. So this is a process of FIFO. Initialize the clock, start the process, reset initialize, and read and write initialize. You have to write first and read first, read next and stop. That is it. So I hope you have understood this entire Verilog HDL thing. This is our FPGA. The FIFO are nothing but the FIFOs are at the end of the designs, and some blocks of memory can also be implemented as FIFO. We'll discuss in the next session. And if you have any questions, please let me know. Thank you.